Thank you very much. I'm Flavio Garcia. I'm going to talk about automotive security, which is a topic that came up, I think, in every single talk today, which makes me very happy because I think we need to talk more about that. So the automotive security over the last decade has undergone a massive transformation, going to this beautiful mechanical car to this beautiful digital car. And almost every single bit of it has changed drastically. And the automotive industry has quite a bit of inertia in the way of doing things. I split this in the mechanical world, in the software world. And traditionally, car makers used to rely on the tier one suppliers for quality and testings and shift responsibility also to them, that they deliver a good quality product. And the idea of testing is, well, let's smash this car against the wall and see what happens. But this doesn't work quite well for software. And there's also a change in culture. In the software world, we are really used to, we provide this without any responsibility, use it as at your own risk, and good luck with that. And there's also this culture of patch, release now and we will patch later. It's a much more quick-paced environment. And so I will enumerate some of the challenges here. Automotive security has kind of all the ingredients for a nightmare, really. So we have real-time critical functionality, really life-threatening, together with one of the slowest networks that we have. So you can buy a toy with a gigabit LAN today, but the high-speed CAN bus has up to 1 megabit per second speed. And something that is really worrying is this black box integration. Car makers are large system integrators, and they are doing their best to put together these pieces that they get from the likes of Bosch or Delphi Automotive. They get this black box, basically, which should comply with some specification, but basically they pretty much only have their word for that. And this is a problem with automotive security, because security is in general not composable. You have two boxes. This box is secure by itself. This one is secure by itself. You put them together. You don't really know if you have something secure. That's not how security works. So obscurity in this whole area, in this whole sector, is a big problem. And you have all this tension between different sectors where you have right to repair legislation. So basically, every garage around the corner has the right to service your car, to fix it. So how do you do key management with that? Does everybody has a key that you don't get too much about it? Car tuning is it even ethically unclear whether a car owner should be allowed or should be able to tune their car. It's his own car, he bought it, it's his property. What happens with the liability? Do we want to prevent that from happening? Do we want accountability for it? So how is this all going so far? Well, I would say here that it's not going so good. Security is a market for lemons. And this is a term used to describe a market circumstances where if consumers are unable to assess the quality of a product, they just tend to buy the cheapest one. Because, if everything looks alike, then you say, well, okay, this one costs half of that, so let's go with that one. And that's a big problem, especially when there is lack of transparency by the suppliers, when everybody's selling, unbreakable security and 110% safe products. I will give a couple of examples of this. We looked into vehicle immobilizers. As you might know, it is mandatory that if you want to sell a car in the EU, you need to fit your cars with a cryptographically enabled immobilizer. What that means is a bit unclear, of course. What cryptography, is widely undefined, but we will see about that. So you should not confuse the immobilizer system with the remote control for the doors. They are completely different systems. One is a passive RFID tag which doesn't have a battery, it just authenticates via RFID with the car. And then the remote control, which is battery operated and transmits a much larger distance, and it works even also at a different frequency of 433 megahertz. So we look at a particular chip which was used at the time of the research by all these brands that you see here. High-Tech 2, which is manufactured by NXP Semiconductors. And it's used in all these cars. or at the time of the research, it was used in all these cars, which are basically half of them. And so this is a tiny transponder, which is, it's the little bit that you see there. So this is a transponder which is embedded in the key shelf, and this will authenticate, your car will authenticate this chip every time that you turn your key, or in the more modern cars when you push this start button. Those are more interesting. So if you look at the website from the chip manufacturer, you will see, adding to Kenny's list of bold statements, you will see this: unbreakable security levels using mutual authentication, challenge response. Okay, so we dug into the product, and we look at the authentication protocol, which is here. As you can see, it's very standard. The car says authenticate. The key fob sends his ID. The car will send a random number, a nonce, and an encryption of something that depends on this. And then the more important part, the transponder will send an answer to this challenge. As you can see, there is no randomness coming from the transponder. There is no challenge from the transponder to the car. So there is no mutual authentication, as it was claimed. So then we look into the Cipher that it was used, and this is quite a simple cipher. It's a typical design from the 80s, beginning of the 90s, where you have an LFSR on the top and a Boolean function below. This is a stream cipher, so this, with every clock tick, this generates one bit of key stream, which is then XORed with the plain text to produce the ciphertext. So we found a number of weaknesses in this cipher. One of these is that there is dependencies between different sessions. If you authenticate 2 times, the cipher state should be completely randomized, but the random nonces are only 32 bits. But the internal state of the cipher is 48 bits. So there are 16 bits there on the left that remain persistent throughout several sessions. And that's, if you're an attacker, that's very helpful, because you can run several sessions and learn information about the key, which is consistent, which is persistent there. Another weakness is that this is a Boolean function, as I mentioned. So this Boolean function has the particular feature that one quarter of the traces, 1/4 of the authentication sessions, this bit is ignored by this Boolean function. This is a property of just for being a nonlinear function, so it's a very imbalanced thing. So basically, 1 out of 4 times you win the lottery, and you get an authentication trace, which only depends on the green part of the internal state, and this facilitates a guess and verify attack. So you can start guessing bits from the left there, and then because this is all ignored, you can just guess a fraction of those bits, and then verify on the key stream that you got. And then you can recover the secret key out of that. I will not dive too much into the details of it, but because you have to be lucky a bunch of times, then you need 134 authentication attempts from a car, which you can gather in about 1 minute. And then you need 5 minutes computation to crack the secret key. So in total, 360 seconds, which gave name to our paper that is done there. So I will, for this, we use this device, which is called Proxmox 3, which is a RFID tag and reader emulator. So you can eavesdrop this communication and then perform this attack. This device costs something like $200, and you can buy it online. I will show you a little demo. I hope that the audio will be okay. So this is a BMW 1 Series, which we chose. It's just one of the cars from the list there, and we chose this one because it has this start-stop button, which was from one of my colleagues. So we didn't want it to, really force the lock, the mechanical lock into the car. So let me see. So this is an empty key shelf. It's just a piece of plastic to activate the mechanism there. No electronics in it. Oh, sorry. No. How do you? Oh, there we go. So we have previously run the attack. So because 360 seconds is like 1/3 of my talk time. So this is the fun part where you're using this emulator here, and then the car thinks, okay, the legitimate key is in there, and now it says, oh, no, I cannot find the key now. And you put it back there. You can see the dashboard already reacts. It says, it's all fine. And then this takes a while. I don't know why it's so slow, but it's going to get there. Yeah. So I'm not sure if you can hear that, but the engine is on. You can see the speed there. Once that the engine is on, it will keep on running. So you can really drive away now. Okay. So when we found this, we notified the chip manufacturer and XP. We informed them. We gave them 6 months. We kept it confidential, following standard responsible disclosure procedures. They got a bit upset with us. But yeah, so that's the. I think we cannot avoid having security vulnerabilities. I think, what we can do is respond responsibly, and the difference between a good company will have a procedure to deal with this in an efficient way. That's what we need, and we need to be a bit more open about security vulnerabilities, I think. So. NXP at the time of the research also had a chip which implemented AES, and it cost something like 30 euro cent more. So it is not a massive cost implication what we are talking about. And one thing that NXP pointed out is that the attack that we showed is not really a car-only scenario. You need a bit more information. And why is that? Well, as you can see here, if you look what the car really does, the car sends authenticate, and the transponder sends an ID. And the car will have a wide list of IDs there, typically the number of keys that you have. So what will be 2 or 3 IDs in the wide list? And if the ID that you send is not in the wide list, the car will not respond at all. So you cannot get any ciphertext there, this message, which you need for the cryptanalysis. So then you're in trouble. So what you can do is, well, take this device when the car owner is sitting drinking a pint in a pub. You walk close by them, and the transponder, you just send an authenticate message, and the transponder will tell you his ID. But you have to be in close proximity to the victim. This is very short range. This is like 3 centimeters range, so you have to be fairly close to the guy in the pub, which you would like to avoid, maybe. So we got a bit back to the drawing board and decided to look at remote keyless entry. Remember when I said that this is the remote for the remote locking for the doors. Well, I said that this was a completely different system, and it is, but that's not always true, because some manufacturers, chip manufacturers, decided to make a hybrid chip, what is called hybrid chip, which the same chip includes an immobilizer chip and also a remote keyless entry chip, all in one. And it turns out this is the protocol. It's very simple. It's a one-way protocol. This is an active. So this will, as you know, you can transmit for up to 100 meters or like 300 feet away. And it basically sends an encrypted counter. And the car has a window for which counter values it will accept or not. to open the doors. But as you can see here, it sends an ID. And this is encrypted with a totally different secret key than the one used for the immobilizer, which is very good. As we all know, we shouldn't reuse the same key for different applications, so they got that right. But this ID here happens to be the same ID that is used for the immobilizer. So the only thing that we needed to go to the pub to get from the guy while it's in his pocket. Now you can just be close to the car. When you lock your car, you will send this ID over the air, and then you can get into the car and run the attack that I just described, because now you know what the ID is. Okay, so I will show you a very, very short demo. So that's my car there. And that's this little device which I built myself. This is basically an Arduino board with an RF and a RF transmitter and receiver. You can build this for like 30 pounds or so. Pay attention because it's like 12 seconds. As you can see, now it's working. You push the button. And my car over there blinks. Now it's open. Now it's closed. Okay? Also using a weak cipher. So if you can eavesdrop when you lock the keys or when you open the keys, you can get the key for opening and for opening the doors as well. Okay, so that's about the semiconductors that are sold. Now, how about the integration done by the car manufacturers? How are they doing? Well, here you have an example, or a few actually. These are 32-bit random numbers. This is from the immobilizer system, the previous one. These are actual numbers that we observe coming from a French car. There you have the random number. So here you have a list of them coming out of the car. I think you see the pattern. And you can even see, so that's, like, as Kenny mentioned, random generation is something that we know how to do. We just have to get it right. And you can see even what the bug here is, right? This is probably a byte array, and a pointer to the first element is what is being printed and is missing to iterate over the array. And so it's a typical C programming bug, I would say. Huh? This is another French car, another make. This is a bit more subtle. I don't know if you can see the bold font there. But you can see this pattern here. If zeros, ones, Bs, 8. So the second nibble of each byte. So the first time it defines what the other are. And you can see here you have 5, A, C, D. So that's clearly not 32 bits of entropy, what you get there. Now the bug is a bit more subtle. I have no idea how you program that. Because the left nibble looks random to me at least, but the right one is obviously not. I cannot think of any programming or common programming mistake that will result in that. But okay, we'll see. A Korean car using the default password for the chip, this Micronas, and the secret key. This is a bit of incidents we found while recovering some keys. Then you come across keys of this form, with a lot of 1 and only like 3 bytes of random looking bits. So, are you still looking forward to get a self-driving car? I don't know. I think we have to iron a few things before we get there, especially on the security side. There are examples by others, as some of them were mentioned today as well. Checkaway et al. Showed that he could exploit a buffer overflow on the CD player, which would take then control over the CD player, which is connected to the CAN bus. So through the radio, you can inject control messages into the CAN bus and make the car brake or accelerate or whatever you want, really. So that's scary. And there is no good reason, as far as I can tell, to why you should have such an interconnection between critical functionality and entertainment. Well, then Kosher, it also showed that once you have access to physical access to the car, to the OBD port, you can pretty much reprogram every car and get them to do whatever you want with them, like program them for, at midnight, the brakes will stop working and things like that, very scary stuff. So where can we go from here? Well, we need to secure the critical functionality in the CAN bus. This is like having a big network where everybody can send control messages to everybody. That's not fit for purpose anymore. And there, yes, so the key goal there is authenticity, and the key challenge is key management for when you have right to repair. Other suppliers can bring third-party replacement parts. So how do you do key management for that? That's really a difficult problem, and the same problem arises on vehicle-to-X communication, vehicle-to-infrastructure, vehicle-to-vehicle communication. How can we do secure key management for that? And secure firmware upgrades, which were also mentioned today by some of the other speakers. So to conclude, I would say that we need to move away from obscurity. That's often used to cover bad designs and poor implementations, and we don't get extra security from it. And yeah, the kind of mistakes we found, it really feels like 90s software security. It's nothing really revolutionary in here. There are really mistakes that we know how to do better. We know how to build better ciphers. We could use AES for authentication. We don't need to do that anymore to these ad hoc ciphers. We know how to do random generation. There are not fundamental problems that need to be solved. We know how to do it. We just have to implement them and get it right. So I guess that's it from here. Well, I would understand that if you have network access or something, but the immobilizer, you have to be within 3 centimeters from the car. So I wouldn't understand why would you have like a weak random number generator there when you have to be in the car to be able to exploit that. So regarding the weak keys, maybe some companies decide to simplify the key management and have some patterns in the keys, which you can derive from the license plate or the VIN number. But this is all conjecture. I don't have evidence for either way. Yeah. Yeah, well, I mean, you could have a firewall in between. The problem is that now, if you look at this Tesla, we have a beautiful, like this LCD screen, where basically you can tweak the suspension. You can, the level of integration is so high that, if you have a fancy car, you can tweak so much settings from the hardware side, from the suspension, from the brakes, for how the gearbox shifts. So it's also so heavily integrated, and the CD player is it just plays. The interface is also there. We don't have CDs anymore. It's just drawn in the same screen. So, yeah, it is. I think we need that, but I see where the difficulties are. Yeah. Yes, we have. So when you do responsible disclosure, it is very tricky, in the sense that if you inform the semiconductor company, how can I say it? I'm not sure who are the users of a certain chip, like this high-tech 2. I have experimented with colleagues' cars, with volunteers, but I don't have a Lamborghini or none of them have a Ferrari around. So it's hard to determine who is really using a particular chip or not. So the approach that we have taken in the past is just notify the chip manufacturer and strongly encourage them to inform their customers and distribute this information back down through the chain of sales. They know who they have sold the chip to. It's hard for us as a computer scientist, researchers, to know who is really using that. And we have found later on always surprises of usage of some chips that you didn't expect in the beginning. So I think that responsibility should lie on the manufacturer, so the problem owner. So that's why we try to identify who the problem owner is and inform them and encourage them to inform the end users. I agree that there is the times are different than in software. But when we inform about these vulnerabilities, many car manufacturers change their chip in the next 1 or 2 years. So we have seen some impact of the research and some reasonably fast changes for considering the industry we are talking about. So we have chips, immobilizer chips that run AES for many years before this research was done. So I think it was technically possible to have better chips at the time of the research. I think it's also a business decision. There are costs involved. So it's hard to tell. Really.
Right. Thank you very much for that.
Thank you.